In this set of slides, we're going to continue on with our discussion of data representation based on Chapter 3 in your text. We've already discussed issues of data representation and its relationship to processing technology, and we've discussed the use of binary numbering systems, why it's a good use in modern computers, both in terms of its correspondence to two-state devices and its correspondence to Boolean logic. For better or worse, to really understand this material, you really need to understand how to read values in various binary or octal or decimal or representations, and you really do need to be able to convert from one to another. This is material that a lot of you probably had way back when in some math class in junior high or middle school or high school or possibly in a college class. So it shouldn't be new to most of you, but it's the kind of stuff that people tend to forget fairly quickly. So this particular set of slides, this particular video, I'm just going to focus in on a few of these slides as a review, and you can go back and look over it as many times as you need to. Okay, so let's start off with binary and decimal values, interpreting binary values, and converting between them. Okay. So the first issue is when we're going to represent a numeric value, typically it's going to consist of multiple digits. So for example, if we have a number like say 456, there's 3 digits in that. There's the 4, there's a 5, and there's a 6. And how we interpret each of those digits is a question of their position within all of the digits of the value. Okay. The idea behind a positional numbering system is that when we put a string of digits together to constitute one value, each of the digits is interpreted relative to its position and a weight or numeric value that's applied to that position. Okay. So for example, in base 10, okay, and this is base 10 because I've got the little 10 subscript here, the digit immediately to the left of the decimal point, and there is no decimal point here, but if there was one, it would be right next, just to the right of the 6. So the first position to the left is called the ones position. The next position to the left is called the tens position. The next position to the left is called the hundreds position. And if we keep going left, we'd get thousands and 10,000s and whatever. Those numbers come from somewhere, and they are basically the base of the numbering system, which in this case is 10, increased or with an exponent that is represents the position. Okay, so the position of the 6 being immediately to the left of the decimal point, that's considered position 0. The next position to the left, the one occupied by the 5, is position 1. The next position to the left is occupied by the 4 is position 2, so on and so forth. And we take those position numbers, which start from 0 in this case, and use those as exponents. So for example, what is the value of the 4 in 456? Well, we compute that as the number 4 multiplied by the base of the count of the representation, which in this case is 10, raised to the second power, which is the position within this multi-digit value that is occupied by the 4. So we can compute that as 4 times 10 raised to the second power. 10 to the second power is 100, times 4 is 400. So the value of this particular position is 400. The value of this one is 50, which is 5 times 10 to the first. The value of this one is 6, which is 6 times 10 to the 0. And anything raised to the 0th power is 1. Okay. So that's how we literally interpret these numbers. Well, we don't need, we don't really need to do that for base 10 because we've played with base 10 numbers enough over time that we understand them intrinsically, and we don't have to go through a calculation like this to understand them. But understanding how that calculation works is very helpful when we start dealing with other numbering systems such as binary or hexadecimal. Okay. So carrying forward that basic idea, if I have a binary value, base 2, and in this case I have to have a different value obviously since binary only has digits 0 and 1, and there can't be a 456 base 2. Okay, so here's a multi-digit string 101 that's going to be interpreted as a base 2 value. We have the same sort of calculation here. The main difference is the number that we're using to raise to an exponent, which is the base. Because this is binary, all of these numbers here are 2, just as in the example above, they were all 10. Okay, so the interpretation of this number is 1 times 2 to the 0th, that's this one here. The interpretation of this number is 0 times 2 to the 1st, because this is in the first position. Of course, anything times 0 is 0. And the interpretation of this number is 1 times 2 to the 2nd. This number 1, or this digit 1, is in the second position, and its weight is the base of the numbering system, base 2, raised in this case to the position number, which is the second power. 2 to the second power is 4, so this particular one becomes 4, that becomes 0, that becomes 1. We add 4 and 0 and 1 together, and we get the value 5, represented in base 10. Okay. So that's how we quote-unquote do a conversion from a multi-digit value in any numbering system to base 10, is we go through a calculation like this. Okay, if I was to do this in base 16, if this 101 was a base 16 number, just change that exponent, or I'm sorry, this base, and this base to 16. If I was to say, what is the value of this if I assume it's in base 8, just change that to an 8, that to an 8, and that to an 8, and whatever comes out on the right, that's the value in base 10 of 101 as an octal number. Okay. So I think that pretty much covers this slide. So just in terms of terminology, in the decimal numbering system, our base is always 10, and in the binary number system, our base is 2, and we've seen how we use those in these calculations. Now, let's complicate things a bit. Let's actually throw in a decimal point and some numbers to the right of the decimal point. Okay. So as we said in the previous slide, this was position 0, this position 1, this was position 2, because we assumed there was a decimal point just to the right of the 6 in this value. Well, now we've got the same 4, 5, 6, but we've got the decimal in between the 5 and the 6. What does that do to our positioning issues? Well, now 5 is in the position immediately to the left of the decimal point, which makes that position 0. 4 is in position 1, and note in this calculation down below, the exponents have changed for both the 4 and the 5. Okay. The positions to the right of the decimal point, since this position is 0, this position is -1. In essence, we're just counting, decrementing by 1 each time we go. If there was a position to the right of that, it would be -2. Position to the right of that would be -3, so on and so forth. And these would be the exponents. Okay. So in the case of 6, 6 is multiplied by the base of the numbering system, which in this case is 10, raised to the -1 power. Now, most humans kind of don't immediately grasp the concept of negative powers, but basically what they are is fractional values. Okay, so 10 to the -1st is 1/10. 10 to the -7th is 1/100th. 10 to the -3rd is 1/1000th, so on and so forth. Okay, so the interpretation of this number, therefore, is 4 times 10 to the 1st, which is 40, okay, plus 5 times 10 to the 0th, which is 5. So 40 plus 5 plus 6 times 10 to the -1, which is 6/10. So this is 40 plus 5 plus 6/10 is 45.6. Once again, in base 10, we don't really need to think about these details because we more or less deal with those automatically. Okay. Where understanding this detail comes in useful is when we have to deal with numbers in other bases. So let's take the same example we had previously of 101 base 2, but let's stick a decimal point in between the one on the right and the 0 immediately to the left of it. Now, this term decimal point actually doesn't make sense anymore because decimal implies 10. Okay. And a more correct term for that is what's called a radix point. Okay? And radix simply means the dividing line between the whole part and the fractional part, and it doesn't imply any base in the system. When you say decimal point, you're implying that the number is base 10. When you say radix point, you're not making any assumptions about what the base of the numbering system is. Okay? So how do we interpret 10.1, okay, in base 2? Well, following the previous example, okay, the 1 is now in position 1. Okay, the first one, I should say, is now in position 1. Okay, the 0 is now in position 0, and the 1 to the right of the radix point is now in position -1. So we carried forward the same sort of calculation. Okay, this first value is 1 times 2 to the first, which is 2. Okay, this second one is 0 times 2 to the 0th, which is 0. And this third one is 1 times 2 to the -1, or 1 times 1/2. And so we wind up with 1/2 plus 0 plus 2 yields 2.5 in base 10. Okay. And just as further digits to the right of the radix point in base 10 go tenths, hundredths, thousandths, whatever, further digits to the right in base 2 also represent descending fractional quantities, but it's not moving in tenths, it's moving in halves. So one digit to the right is a half, the next digit would be a quarter, the next digit would be an eighth, the next digit would be a 16th, so on and so forth. Okay. Now let's talk a bit about the issue of numeric range. Why do we even have all these various notational methods? Okay, we know the computer, at least computer today, has to deal in base 2. So why don't we as humans, when we're programming the computer, just write everything in base 2? Well, the problem is this: the lower the base of the numbering system, the more digit positions it takes to write a given value. So for example, let's say, the value is 15. Okay, 15 in base 10. Well, 15 in base 10 can be written in 2 digits, a 1 followed by a 5. 15 in base 2 requires 4 digits or 5 digits? 2, 4, 8, 16, 4 digits. No, I'm sorry, 5 digits. Okay. So what took 2 digits to represent in base 10 takes 5 digits to represent in base 2. Unfortunately, as the numbers get larger, that difference increases exponentially. So for example, representing the number 4 billion in base 10 requires 10 digits, 4 followed by 9 zeros. Okay. Representing the number 4 billion in binary requires 32 digits. Okay. So that's a pretty significant difference. Okay. So why is that an issue? Well, it's an issue for humans because the more digits we got to write, the more likely we are to make a mistake, and the harder it is to read things. For the computer, the implication is to store relatively large numbers inside the computer, we're going to need lots of binary digits. Lots of binary digits. So while when we write numbers, for our own use in base 10, if we're talking about our own budget, usually 5, 6 digits is enough, maybe 7. If we're talking about, tracking the national debt, well, now we need, 12 or 14 or something like that. Okay, but in a computer, 14 digits hardly buys you anything. You'd better have 32 or 64 or 128 if you're going to represent really large numbers. Okay. Now the other issue arises because of these large numbers of digits is one in terms of the efficiency of computer circuitry. Okay, if I ask you as a human to add 3 numbers, 1, 212, and 1015. You don't have much trouble doing that. Okay, many people can do it in your head. If you got to write it down on a piece of paper or a board, we all know the little trick of writing the numbers one on top of another, aligning them with the decimal points to the right, and working one column at a time. It's something we've been trained to do since elementary school, and most of us are reasonably good at it. Okay, but we're not really thrown by the fact that the 3 values we're adding together each have a different number of digits. Well, surprisingly enough, possibly to some of you, that sort of flexibility is actually very difficult to implement inside computer circuitry. Okay, computer circuitry is actually much simpler if all 3 numbers we're adding have the same number of digits. Okay, and what that tends to mean is that we wind up pre-padding a lot of our values with zeros. Okay, and that's simply to make the computer circuitry simpler, and a recurring theme we'll emphasize in this class over and over and over again. Anything you can do to make computer circuitry simpler makes it faster. Okay. and fast is usually something we want inside computer circuitry. So much of computer circuitry design is doing things to improve efficiency, to simplify the circuitry itself. Basically, the simpler the circuitry is, the fewer components, the fewer wires, the less distance for the electricity to travel. And when we're talking about electricity traveling at a constant rate near the speed of light, distance equals speed. Okay, or I should say, distance equals the inverse of speed. Okay, the shorter it is, the faster it is. So this fact that computers are restricted to binary numbers has a quote-unquote cost. The cost is lots of digits. Okay, one way of dealing or minimizing the impact of those digits, at least inside the computer, is to ensure that every piece of data of a given type, integers, reals, whatever, uses the same number of bits. Okay, and that of course means we have to define what the maximum number of bits we're going to need is. And any numbers that are considerably less than that are going to have a whole lot of leading zeros in them to quote-unquote pad them out to match that same number of bits. Okay, so what numbering systems might we use besides binary and decimal? Well, when we get into really big numbers like memory addresses, okay, even decimal becomes kind of long to deal with. So, for example, 4 billion is 10 digits. 4 trillion, quite a few more. And when humans have to deal with values that have that many digits in them, they tend to make a lot of mistakes. Okay, so there have been other numbering systems used in the past, and some that are still used. Okay, in particular, octal notation was very common in older IBM mainframe systems. Okay, note that octal has no advantage in terms of length compared to decimal, but it has a big advantage in length compared to base 2 or binary. One of the advantages, quote unquote, of dealing with octal as a means of shortening up numbers as opposed to decimal is that base 8 is an even multiple of base 2. Okay, 2, 4, 8. Okay, so the conversions back and forth between octal and binary are a lot simpler to do than conversions between decimal and binary. That said, back in the 60s and 70s when IBM ruled the world, the fact that its mainframes use octal pretty much meant, everybody else had to use octal, and as long as IBM pretty much ruled computing, that was the case. But IBM's stranglehold on computing pretty much broke down during the 80s, and octal kind of went with it, except in the IBM mainframe world, which is now a much smaller piece of the computing world than it was 40 or 50 years ago. Another approach very commonly used outside of the IBM world was hexadecimal. Okay, hexadecimal is base 16. And that sounds kind of strange because in our written language, at least, we only have 10 digits, 0 through 9. So what we do to get the extra 6 digits is we steal the first 6 letters of the English alphabet, A, B, C, D, E, F. So this is 0 through 9. A is 10. I can't seem to get out of select mode here yet. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay, so if we want to write the number 15 as a base 15, the value 15 base 10 in hexadecimal, we only need one digit, F. Okay, hexadecimal is a doubling basically of octal. So once again, we've got an even multiple of base 2, which comes in handy sometimes. Hexadecimal is very commonly used when we write out memory or storage addresses. So, for example, the memory address of the 4th gigabyte in your computer, or the 4 billionth storage block inside your disk drive, that would be a 10-digit number. Excuse me, that would be a 10-digit number in decimal, but it's only a 4-digit number in hexadecimal, which is pretty nice because it makes it's much more compact to write. Alright, so that concludes our discussion of the alternate numbering systems. As I said, this is not information you tend to use directly, but it comes up on fairly regular occasions, particularly if you do any systems programming, particularly if you're trying to interpret, for example, error messages, which often include hexadecimal addresses, okay, or sometimes will include binary bit strings. Okay, so it doesn't happen often, but depending on what job you're actually working with, you may or may not have to deal with hexadecimal numbers or binary numbers, and so it's a skill you really need to have. Okay, that said, but let me finish this discussion here with one particular observation. If you don't like doing this stuff in your head or on pieces of paper, there is an alternative. If you simply open the standard Windows calculator, which is right here, okay, and see I've already got mine set up. You've got multiple views here. Okay, this is usually the one you'll see by default, standard. Okay, but there are other views. Okay, there is scientific, which gives you all these funky trigonometric functions and what have you, and gives you some roots and some powers and a few extra memory functions. Okay, there is statistical view, kind of handy if you're doing statistics, and the one most relevant to us is programmer view. Okay, and the nice thing about programmer view is it allows you to work in binary, octal, decimal, or hexadecimal, and allows you to pretty freely convert between the two. So for example, if I take a decimal number, say 456, okay, and I want to know what its representation is in binary, I just click decimal, type in 456, and then click binary, and there's its representation in binary. So note that 3-digit number in decimal took 9 digits to represent in binary. Okay. Likewise, if I want to go to hexadecimal, here let's take 4 billion, so that's 4,000 million billion. Okay. Convert that to hexadecimal. Note that string just got a fair bit shorter. Okay, and of course as I get up into terabytes and what have you, it gets even shorter than that. So I don't expect you to to do these things by hand any more than I expect a student in finance to sit there and crank through complex finance formulas by hand. You got a simple calculator here built into Windows. I would assume there's other ones on a Mac that are similar, or a free app you can download or whatever. So the bottom line is if you've got an application that'll do this work for you, use it. That's what it's there for. Okay, that concludes this part, and there will be some other parts associated to this chapter, but so much for this video for now.